In this video, we take a first look in the curve fitting toolbox. This video is based on the script example Polyfit. We will demonstrate polynomial fits. So let's start in line 2 with the usual preamble. We can have a quick look into the preamble, which is mainly setting of defaults, defining some format specifications, and defining an inline function and an abbreviation for the string inline. For teen, we also set the random number generator to its default algorithm and start at the default seed. Let's return to the main script. As I said, I will demonstrate first the curve fitting toolbox with fitting polynomials to data, polynomials of various degrees. I will start with data that are actually generated by a polynomial function plus some noise. So these data contain 12 data points. The independent variable x varies in the interval from 0 to 10. We'll also extend that interval to see whether we can meaningfully extrapolate from the fitting polynomial. This is the functional form of the polynomial, and in line 12 we define the standard deviation of the noise, which will be a normally distributed white noise, and its standard deviation is set to 1. In line 21, I define the vector of x values. It's a regular grid of values. This is, of course, not obligatory. The x values could be anywhere in the interval. Please note that we have to use column vectors for the functions in the curve fitting toolbox. So I have to transpose this vector to a column vector. Now we have a loop where we try polynomial fits of different degree. We start by asking for the degree. Let's start with degree 1, which means a straight line. So we fit a straight line to the data, probably not a very good fit, but we will see in a minute what it looks like. Let's open a figure to plot the true data and the noisy data and the function itself. In line 44, I add normal uncorrelated noise by using the function norm RND, which generates normally distributed or Gaussian random numbers. In this case, the mean value are the true values and the sigma is 1. So let's see how far these noisy data deviate from the true values. Yeah, in figure 1, we see the green line, the true function. The green circles are the true function values at the chosen points of x. And the blue stars or pentagons are the observations. So that's the noisy data. And we will now fit a polynomial of degree 1, a straight line, to this data. We start by defining a fit type. The curve fitting toolbox has a quite large library of predefined fit types. And in this way, by calling the function fit type and the name of the predefined model in the library, which is poly1 in this case, this character vector evaluates to poly1, and poly1 is a predefined model in the library of models for curve and surface fitting. Let's have a quick look at this list of models. So I will now call the web function and switch to the browser window. Here we are. So here we have the list of library models. Let's concentrate for the time being on model types for curves. We'll talk about surface fitting later. These models contain both parametric and non-parametric models. At the moment we're interested in polynomial models, which are of course parametric. For a polynomial of degree n, we have n plus 1 coefficients or parameters, which can be adapted such that we get the best fit of the polynomial to the data. We'll talk about some of those a bit later in another video. So let's now return to the command window. Now let me first show you the polynomial models. These are the models shown here. You know what a polynomial is, and they are predefined for degrees 1 to 9. So they are models poly 1 to poly 9. At the moment, we use the model poly 1. So let me switch back to the Matlab window. Okay, now we have a fit type, which is poly 1. We have the data in the column vectors x and y. And we now can invoke the function fit that takes x, y, and the model, the fit type, as arguments and produces an object myFit, which contains the fit results, and a structure myGov, which shows various measures of the goodness of fit. Let's first have a look at the object myFit. So myFit is an object of class CFit, where CFit stands for curve fit. There's also class SFit, which stands for surface fit. Now let's have a look at some of the contents of this object. Here you see the most important output, which are the fitted coefficients, P1 and P2. Please note that the numbering of the coefficients is in descending order of the power of x. So P1 is the coefficient of x, and P2 is the constant coefficient. We also get confidence bounds for these coefficients, which means that if I would repeat this fit many times with the same distribution of the noise, then the coefficient P1 would be in this interval with 95% probability, approximately at least. Okay, so let's now have a look at the goodness of fit structure. This has the following fields: the squared sum of errors, then r squared, which is called the coefficient of determination or Bestimmtheitsmaß in German. We have the number of degrees of freedom, which is just the number of observations or data points minus the number of coefficients that we have fitted. We have the adjusted coefficient of determination, and we have the root mean square error. How can we interpret these results? Well, first of all, the root mean squared error is just the sum of the squared errors over the degrees of freedom and then the square root of this quotient. How can we use these numbers to judge the quality of the fit, the goodness? Well, R square should be as close to 1 as possible. R square equals 1 means a perfect fit. So no residuals after the fit. And the RMSE, the root mean squared error, should be as small as possible. If you want to know more about the goodness of fit and the interpretation, I direct you to the website which is given in line 61. Let's just remember for the time being, R square should be close to 1 and RMSE should be close to 0. Now we come to a very important point. How do we get more results out of the myFit object? There is a function plot, which is a method of an object of the class CFit, as you can see in line 63. And I want to show you some of the things you can do with this plot function. So let's go to the web page again. Here I have to switch to the browser page, browser window. Okay. This is maybe not easy to read in the video, but let me try to increase the font size. Yeah. So the syntax of this plot function is, let's have a look at the line plot of CFit. The first lines are for surface fits and the following lines in the syntax sections are for curve fits. So the simplest call is just plot CFit. Let's now go down to this section for curves. And here you can see you can plot the fitted function. You can plot outliers. We'll talk about that later. And you can plot predictions and residuals. So you can, for instance, plot data and fit. That's the default. Then you can plot the data and the fit with prediction bounds for the fitted function. You can plot data and the fit with prediction bounds for new observations. These are wider bounds, larger bounds. You can plot the residuals, so the differences between the observed values and the fitted values at the given x values. You can plot standardized residuals, derivatives, and integrals. So let's use some of these options to learn more about our fit. I switch back to the Matlab window. So let's just plot the fit itself, which is a straight line. So the red straight line is a fitted polynomial. You see, of course, it's a very bad fit. We cannot expect to fit data which are generated by a third-degree polynomial by a straight line. So the residuals will be very large, and we see this in the next plot. So the blue triangles connected by the dotted blue line in figure 1, these are the residuals of the fit, the difference between the function value and the observation at a given x value. We also see that these residuals look highly non-random. They follow a rather well-defined curve, so we can assume that this fit is not good at all. We also see at the goodness of fit values that the fit is bad. R square is only 0.66 and the RMS E is huge, it's larger than 6. Right, so the blue triangles and the blue dotted line, these are the residuals. Some of them are negative, some are positive, but they do not look random, which means that there is some systematic effect in the residuals. Next, let's look at a prediction. So we extend now the interval to a larger x interval. So we set now a larger limits in x from -2 to +12. And we now fit the prediction for the function. So the red line is just an extrapolation of the fitted line to the larger interval. And the red dotted line, this is a prediction interval and 95% prediction interval for the function. Now I've also plotted the prediction bounds for the observations. So we expect a new observation to fall in this wide range between the prediction bounds, which are drawn in a red dashed line. Let's finish this. Okay, now we see again in the legend in figure 1 the true function in green, the observations in blue, the fitted line, a red line, the prediction interval for the function, the red dotted line, and the prediction interval for observations, the red dashed line. It's obvious that this is a very bad fit, so let's try degree 2. Let's step up the degree by 1, and now I go directly to line, so we are now in line, let me see, where are we? We have done the fit, we've plotted the residuals. We are now in line 75. So please go to line 75 in the script. Here the script asks for a carriage return to continue. Let's first have a look at the fit with polynomial of degree 2. You see it's still not a very good fit. The residuals are still rather large and they have a clear functional form. They do not look random at all. In a good fit, the residuals should look more or less random. So let's continue to see the prediction interval. Let's step to the end of the loop. Okay, you still see that the prediction intervals are very, very large. So if you want to extrapolate from this fit, you will get very, very large uncertainty. Okay, next fit, degree 2. In this case, we can accept a much better fit because we know that the data were generated from a polynomial with degree 3. So let's enter 3. Now things look much, much better. If you look in figure 1, you see the red fitted polynomial is very close to the green one. The residuals are much smaller. They don't show a clear functional form like before. They do look more or less random. They're both positive and negative. And the R square is now very, very close to 1. If you look in the command window, you see an R square of 0.9957, which is a very, very good fit. This means that the fit explains a lot about the data. If R square is 0, the fit doesn't explain anything. If R square equals 1, then you have a perfect fit, and the fit perfectly reproduces the observations. This is not the case here, of course, but you see that R square is very close to 1, so we have in effect a very good fit. Well, no surprise, because the data were generated by just a polynomial of this degree. Okay, let's continue to have a look at the predictions. You see that now the predictions intervals are much smaller. So if we extrapolate the fit, which is always a risky thing to do, we see that the uncertainties are now much smaller than they were before. I have to warn you that extrapolation of a fitted polynomial can indeed be very counterproductive, especially if the degree is too high. Then the behavior of the polynomial outside the range of x can be very arbitrary, difficult to judge. So let's try degree 4. I will now go a bit faster. So we have now degree 4. You see that the polynomial is not much different from before. Obviously, the fourth order term is very small. If we will look at the coefficients, you see that P1 is 1/1000, 10 to the minus 3, so it's very small. The R square has not changed much, still very close to 1, still a very good fit. But now you see that the extrapolation is worse, because we have now an additional coefficient which is not really necessary, and this tends to blow up the errors outside the interval of the fit. Let's go on to degree 5. You see that the R square is even closer to 1 than before. The RMSE has become smaller, and this is what we call an overfit. We have now 6 coefficients, and the polynomial now tends more and more to reproduce, to follow the data points instead of finding a good fit to them, which does not have more coefficients than are necessary. So this is clearly the case of an overfit, and this gets even worse if we increase the number of the order, the degree of the polynomial again. Now the maximum is 9 because the predefined fits stop at degree 9. So let's try 9. And now you can see that the polynomial more or less passes directly through the data points. And this means that the extrapolation behavior is very bad. So you see that the extrapolation errors get extremely large. So extrapolating from this is highly unsafe and not recommended at all. Clearly, the best fit is the one with degree 3. Okay, let's now stop this run and let's pass to the second data set, which is a logarithm plus noise. Let me quit now the debugger and start again with the second data set. Let's again start with a straight line. So the functional form is now just the natural logarithm, and the sigma of the white noise is 0.1. The limits are in line 16. They are from 0.5 to 10. And we will look at an extended interval from 0.1 to 12. Of course, 0 must not be in the interval because the logarithm is not defined at 0. But we have now 25 points in the interval, so we have a lot more information. So let's directly go to the results. Let's start with the polynomial of degree 1, a straight line. Again, the green line is a true function, the green circles are the true observations, and the blue stars, pentagons, are the observations. A straight line is not a good fit. Obviously, you see that the residuals, again, do not look at all random. They have a clear tendency from negative to positive and then back to negative. Of course, it's not obvious that we can actually find a good polynomial fit at all to this function. So let's try with some higher degree polynomial. Let's try 3. Now let's try 2 first. Parabola, parabolic fit. Obviously, this does not work very well. You see that the shape of the logarithm is not reproduced at all, and that the prediction intervals are very large. So if you try to extrapolate from this, you will get a very large uncertainty. Now let's try degree 3, a cubic polynomial. The fit is not very good either. Let's have a look at the prediction intervals outside the fit interval. The errors are not that large if you approach 0, but they increase rapidly if you go beyond the upper limit of 10. Okay, one more try. degree 5. This is quite a good fit in the lower range, but then towards the upper range, the fit gets somewhat distorted by some of the points. The residuals do not look that bad. They actually look pretty random. So let's try to see what the extrapolation errors look like. You see that interpolation towards 0 is not particularly dangerous, but interpolation beyond 10, beyond values larger of 10, is very dangerous because the uncertainty gets extremely large, so you cannot trust any values which you get from extrapolating beyond the upper limit 10 of the fit interval. So I will now enter 0 and quit this script, and this terminates this video.